we are good, and this time we are going to start with Merkle trees. Then we can go into some sort of Merkle proofs. We shall see where it goes. And this is a great concept in the blockchain space. So we know that blockchains are decentralized, meaning that in a way everything can be built everything is built and also used by decentralized teams. So things like building clients is a thing in the blockchain space, whether building clients that will be used by node runners or miners. Yeah, it's one of the things that is very prevalent in the ecosystem, and understanding concepts such as Merkle proofs can help you become one of the researchers and do great things. So I think I can share my screen. Let me turn off the live. Otherwise, probably before I start, maybe I can ask, but if there is nothing, those who went to the Lisk Roadshow, yeah, welcome back. Yeah, and hope the sessions are moving on well. So share screen. Okay, all right. Okay, so we are going to begin this topic from a high level, and what I mean by a high level is we are going to begin with use cases in smart contract. Then we go deep into the components that are used to build the blockchain architecture itself. One of the things that we miss as I think Africa, we have a few people who are doing great in this field, is our contribution to protocol levels. Yeah, so I think this is mainly because we don't know or we are not exposed to such concepts. And yeah, so today we are going to be having this discussion. So Merkle trees. Can you also record? Gundio. Okay. Bibanga. Okay. Ate we recording of recordings in iPhone or earphones was like ate muli was. All right, so yes, we are going to really I'm going to be getting stuff from different places. First off, let's go to the Rise Up. So our Rise Up is why? Omba basobola okujja ne mutuule. Like some oba omu natuula eno atula babiri like notula eno nange. So yes, you can, today's date is it 10th? Yes, it is 10th. So 10th, what do we start with? Is it the math 310 or 10-3? 310. So 2025. Feel free to put your name and handle in the rise up. Yeah, also I encourage others to follow each other, whatever someone tweets. So today I have really many sources to tackle, but I'm going to go between to one. We're going to start with Merkle trees in smart contracts. So in smart contracts, this is one, and then two, in building of blockchains. So we're really going to be these are the two modules, two mechanisms we are going to look at. I don't know why this is I just put two. So why do we talk about this? So in our last session we had talked about a scenario. Let me share the rise up and the part in the let me share the rise up in the here. Yes, please, you can add some of your info so that others can follow you. So why is this very required? In smart contracts, they really help us to reduce the gas costs. So last time we saw building a smart contract that requires you to have a whitelist address, and whitelist addresses are used in many scenarios. During airdrops, the protocol should have a list of the addresses that should be airdropped to, stored somewhere. Doing other things like maybe an NFT exclusive launch, exclusive mint to the people who are inclusive of the club and things like that. But it is not ideal to store these addresses on chain. So what you can do is store some sort of a Merkle tree that can help you get all the addresses without having them stored. Yeah, so that's the thing we are going to first look at, the example. I'm going to take courtesy of, I think that was best explained here. Okay, so for us to move, I think together, I'm going to have these, and then and then keep explaining. I think this will work for now. If it doesn't work, then we can see another mechanism. So have this article. Today I have very many articles, but I think I should also share it in the rise up. My main aim for this is for us to get the concept, I think, first, and then also get in detail with time, if time allows. You can intercept me if I'm moving fast or you are not understanding something. So this article explains how to obtain and what Merkle proofs are. Merkle proofs are used to decide upon the following factors: if the data belongs in the Merkle tree, to concisely prove the validity of data being part of a data set without storing the whole data set. And this is one of the concepts that we are looking at, also to ensure the validity of certain data set being inclusive in a larger data set without revealing either the complete data or its subset. This is one of the researches that has been happening, things like ZK and optimistic rollups. Yeah. So Merkle trees make extensive use of one-way hashing. Merkle proofs are established by hashing a hash's corresponding hash together and climbing up the tree until you obtain the root hash, which is or can be publicly known. Okay, I think I'm going to be sharing between resources, so I think there is a lot of information that has been shared in that, and I'd love to add on from here. Okay. So I think specifically for the example we had, I think this has really abstracted many things. So I felt I should break it down probably a bit. Also, I can share this in the Rise Up. I think the Rise Up works better because data is not erased after the... Is it the same? Oh, I wanted to copy this. Command C. Today's Rise Up might be full, but hopefully you get time to go through many things, through some of those articles. Yeah. So, as we have seen in the previous, I think there are some concepts that were maybe skipped. But here we can start from what is a Merkle tree. A Merkle tree is a type of hash tree in which each leaf node is labeled with the cryptographic hash of a data block, and each non-leaf node is labeled with the cryptographic hash of its child node's labels. The majority of hash trees implementations are binary. Each node has two child nodes, but they can also have many more child nodes. Okay, this is a typical. So, yeah, the biggest thing to get from it is simply what really a Merkle tree is like a tree inverted. So, the one that is up here is the root, and what is down is the leaves. So we are going to see how this data abstracts. One of the things we realized initially is that when you hash data, a blockchain does data hashing, whereby if I have any amount of data, maybe 2 GBs of data, and I put it through a hash function, I take it through a hash function, then I receive a hash of the same digit. So I receive a hash of the, not of the same digits, but of the same number of letters. Is it number of letters?
Fixed length.
Yeah, thank you. Hash of a fixed length. Yeah. So you get given hash of a fixed length. No matter which amount of data you are inputting, whether it is one letter or a GB of data. And this is one of the biggest needs of blockchains. Blockchains don't need to have to store data due to their nature of being distributed. And we are going to see that internet again. Wena okapini awo. Thank you. Tangayo hackathon endala egula generator. Etanga hackathon egula generator. Omukulu mane. Nga mobilizer. Nga mobilizer. Twagala kukulabirako. Mulimu guyinza okuba omunene. Onyiga bunyiza awo.
Etukola hackathon.
N'otugamba mwe mbatadde no hackathon temukwatako. Nzakola.
Mbuuza compiler.
Kuba data weesimba naye adduka. Oli nateekako omutwalo naye tegwazimalako essaawa ennya. 4 GB. One what?
MTN. Star 16.
Oyina data? Tuyitawo.
Kati tuyita.
Mukwebuza bwe tetuyita.
Mulinako omuli.
But I have 1.5
GB. Hey. Oba tukozese naddala simu yo. Gireete. Tutobe. Nkanguleyo tto.
Ziberemu mwenda bbiri.
Layini eyinaemu. 2 GB. 5. Ekintu kya gundi kino.
Nebaleka balina byebakola kuba gabadde gabuukabuuka.
nteekako nteekamu yiyo. Ne Merkle Profs nazo tezaagala zisomesa. What is escaping? Kyokka nno gundi recording.
But it has this sense.
Ogenda kujoining nkugobye tukolere kuno kadduka kasimu tekatereka muliro era mbagobeza speed naye next time better. Yes, let me connect with my account. All right, so yeah, sorry about the glitch, but let's keep moving. So as we are looking, let me share my screen. So as we are talking, that one of the biggest things that we are having, because of this kind of capacity that hash functions bring on. So if you put the hash functions of trees, then we really reduce the quantity or the weight of the data that is being stored on the blockchain, because what is actually being stored on the blockchain are hash functions. I don't know why this thing refuses to type. Okay. Etherscan. So if I'm just to look on Etherscan, all that we have that is stored in these blocks is actually hashes. So hash everything is all about like these hash functions, and most of them, or if not the basis, all of them are made from Merkle trees and other types of trees like Patricia tree and so on. So it's a fundamental thing that really compresses data, yet leaving it accessible. Yeah, like, so let's really continue on that. I think. So here we are looking at, so imagine I have, so what happens with a Merkle tree is that you have data. I don't know, if I click on X, does it have any harm? Okay. So let's say you have data L1, L2, and L3, and L4. So without some kind of data, a Merkle tree can be formed by hashing this data. But with a Merkle tree, you can also prove that you had L3 when you don't know what L3 was from viewing the hashes. And yeah, we are going to see how that comes about. Okay. I think I should ask what kind of data structure is a Merkle tree? I think it is a tree. Okay. So yeah, so that's what I wanted to get from that. Let me go back here. Yeah, today since I don't have another screen, let me really take us as I want it to be. So here, given that one-way hashes are intended to be collision-free and deterministic algorithms, not two plain text hashes can or should be the same. So Merkle proofs are better explained with the following example. In order to verify the inclusion of data K, so what we looked at mainly here is that Merkle trees are used to verify. And how do they verify? You have data, L1 is data, L2 is data, L3 are data blocks as we're seeing here. And then when you pass them through a hash function, you start getting hashes. And these hashes can be stored in a kind of form called Merkle trees. So in some instances, if you have the hash of the root hash, it's called root hash, which is the top, you could be able to verify that a given data was part of the, for example, if there are transactions or if it was the database without knowing that data. And that's the thing we want to get very well here. So I think with this, I'm going to, I wanted to draw this, but since we have it here, I request us to really okay, so since I've lost what I wanted, I can just keep like ranting about it. So without all these that are in green, blue, HK, HL, HM, NOP, if you only have these, you can be able to sketch other data. Okay. How better should I make it? Okay, let's go slow. In order to verify the inclusion of data K in the Merkle tree root, we used a one-way function to hash K to obtain HK. So there is data K, let me say, which is unknown. And we want to prove that data, for example, this is used in two things. One is the provers and verifier. So it is used in a scenario where I want to say, for example, a worst case scenario is that was this transaction part of the block, or was it part of the transaction that went on in the blockchain? This is how proving actually is done. So when we want to prove that data was part of the block, we first get the hash of the data and then the root, and then start calculating whether that was part of the block. So that's one of the use cases of Merkle trees, and I think we are going to see this very well. So in order to validate the inclusion of K doesn't have to be revealed. Similarly, the hash of data L can be revealed without any implicit security repercussions. We are going to know how it works. So hash of K when hashed with the hash of unknown data L. So we want to prove that K was part of the Merkle tree or was part of the data, because what is stored in our block space or in our blocks are hashes. Am I moving so fast? All things will be clear as we move. I wanted to draw these proofs, but I think it will take me some time. So let me just explain. So a hash of KL hashed with, okay, this is not a good example, I think. Okay, so yes, I think what I wanted is here. So maybe before we go to that huge thing, we can look at some diagrams of a Merkle tree, though converted upside down. So this is the root, and the nodes, and the leaves, and the data. So if I have my data A, B, C, D, E, to get the first leaf, I will hash A, which will give me hash 1 will be hash of A, and hash 2 will be hash of B, and hash 3 will be hash of C, likewise. So now if I'm to combine these two hashes, and why should I combine these two hashes? Because the use of this root is to have a very compressed. One of the things we say that as long as you hash the data that you have, you'll have the same output length, and that will significantly reduce the storage that you're using, because one of the downsides of blockchains is storage. So to get H6, I'll have this hash of A plus hash of B. I have this hash, I have hash A plus hash B, which is H1 plus H2, and H7 will be H3 plus H4, and these ones that cannot be combined will just keep going. Yeah. So to get H8, I have the hash of when I add these two, which was hash 6, and something like that. So all these hashes are having the same data length. And do we understand what I mean by data length? From this concept, whatever we hash, when we hash a hashed output, we shall get a hash of a fixed length. And the reason the first reason is to reduce the storage used. And the second reason is also to quickly iterate over the data. So if we could prove that, for example, data A or B or C was part of this transaction without revealing the transaction, because what we have is hashes, and hashes are one-way function. So with the same data, you get the same hash output, but it is not vice versa. Okay. So I think there is some quite understanding up that point. Now I don't know if I have feedback. Do you have a question? Yes, ask.
Would you please pardon on the hash thing?
Okay. Thank you. You had what website gyewangamba yali gye twagambye ku hashing? Okay. So no, I think kakodyo kapya. So if I have this data, there is a website that we use for hashing. So I've just got a random website here, H5 used for hashing. So one way of hashing. So if I write something, I'll get generate. I'll get that of the same length, but I can use, I think there was some hash generator for blockchain. I think, let me see, hash. So does anyone remember that website? I usually forget it. Sometime back Emma used, I think it is this one. Yeah. HH8256. So there is this website. Let me put it in the rise up. The rise up is also rising up. Okay, so as I put it there, I think we can first continue. So this is one place where we can actually go through how we generate a hash. So we start with, there is a hash here when I have nothing in the data. When the data is empty, if I put in 1, I get another number, unique number here. If I put in 12, I get another unique number. This is a hash, but this number is of the same length. Even if I add here a full document, yes, the number down here changes, but it is of the same length. So this is a one-way function. There is no function that can decrypt this from this, but whenever I have these ones, they will produce this hash. So that is hashing. So if we go to probably a block says if you have a nonce and a block number and you give a digit and you say mine, what it does is that this will look through which nonce it can generate to have the hash which was similar to the previous hash. So let me say I give 3. The nonce is 9663. So the nonce will change to make sure that the hash, when you add the nonce and the data, the hash that you get will be like the previous hash. What this is trying to implement, that if I make transactions, the block is formed with 3 things: the hash of the previous block, the transactions of the current block, and the nonce. So the current block of a blockchain should have the hash of the previous block should always match the hash of the previous block when it was a current block for the transaction to be proved correct. Anyway, I think I'm going a bit far, but that's it about hashes. And here you can really play around. I think we shall come and I'll just take on this website. So that means that here, if I change something, it shows that from this block on up to all other form blocks, there will be a mismanaging, there will be a mistransaction. Yeah, something like that. There will be a wrong transaction. Okay, let me stop that at that, but that is all about hashing. So what we have in Merkle trees is we are hashing hashes. What I mean is, so I can hash 1 and get this, but I can also hash this. So I can use this as my data and get another hash. Okay. So here we are trying to see how the root is, which is called the Merkle root, is formed. That initially you have data blocks. Data blocks can be a bundle of data. It can be one, but data blocks. And then you hash them to get the first layer of hash, which here is called the leaves. Then you can hash and get the second layer until you reach the root hash of that data. So one of the biggest use case of the Merkle root is to prove that data is part of the given Merkle root without revealing the data itself. And how does that happen? It simply means that if I keep hashing, I'll get the same result. If I get the same results when I hash what has been given to me, if I get the same Merkle root, then this data that has been presented to me is part of that sort of data structure, all tree. I think now with that I can go to this very well. So for example, with this, if I have only HL, HK, HIJ, which is the hash of IJ, hash of MNOP, okay. So I think I can draw this. I didn't want to draw. I drew it in the book, but I think let me draw it so that it really clicks. If it clicks, it's the only thing. So we have A, let me say B, C, D, E, F, G, H, I, J, K, L. I don't know whether these are visible. M, N, O, P. So this is like the data. So this is the data. So the question could be prove that data K or data set K was part of transactions or was part of a Merkle tree, or because this data is stored in terms of hash functions. So mostly what they do is to prove that the transaction was part of the submitted transactions. Even like for L2s to say that now they have submitted a correct transaction, the L1 must run a proof to prove that what the L2 has submitted passes. So I think allow me to really be slow on this so that it is understood. So this is data. These are not hashes, but this is data. So we have data sets A up to P. So to get the hashes of this, we shall have HA, HB, HC, HD, HE, HF up to HP, which is hash function of A. And as we are looking here, that for example, if it were to be that, so the data for A is A, and the hash function of A would be probably this if it is a HA256. So we are going to just represent that as HA and HB, HAH up to. Okay. I think I could replicate this, but no. Yes. So the hash function of A. So the hash function of A, No, the hash. Then we can have HB, hash function of B, hash function of C, Okay, so we have these hash functions. Hash functions are generated by passing these data blocks through a hashing function. This time it could be h8256 or any hash function. So here probably we could put an arrow. Yeah, just an arrow. I thought it would take more time, but I think it is taking less time. So we shall be patient because I think this is a good concept to base on many innovations like trustless bridges and even building other blockchains or layer 2s. So that's it. So for this question, I want to have a question. So in order to obtain a Merkle proof of H, we need HL, HI, HM. We can together obtain. Hence proving that HK was part. So the question could be prove that hash of K was part of the Merkle tree, which will imply that the data set of K was indeed part of the Merkle tree with only this data. With only hash of L, hash of IJ, hash of okay, so if I'm to put it in perspective, so let me draw them here. I'm going to remove this is H of hash of the hash of A plus B. H of A plus H of B, hash of B, which would be, we can give it like one hash, unless I suppose maybe hash of AB. We use the unify factor just like that, but in the real sense it should be like hash of A plus B. So drawing these things is proving to be AB, then CD. Okay, let me AB CD EF DH so okay, yeah, the BC is not supposed to be part The way we form the Merkle trees is that we bring these together, and then we bring these together, and then these together, and these together, GH, IJ.
How about this and this? You skip
How about
B and C.
B and C? Okay, let me finish here and then we come back to that. IJ. KL. So okay, so someone was asking, I've missed B and C. So we don't have to have like B and C here. No, because we are getting this is a hash that comes from hash of A plus hash of B. So maybe hash of A union hash of B, and we have just said hash AB. And then hash of C, so I think
We don't repeat them.
this is what I'm going to do. I don't know how this. How do I remove these lines? I don't know why these lines keep putting themselves there. Yeah, this is good. Maybe I'm gonna put them there. So So initially I have data A, B up to P. So this could be data blocks or it could be a single data, like probably a string or anything. So when I hash A, I'll get h of A, and when I hash the respective data, I'll get their respective hashes. Yes? So to construct the Merkle tree, if I combine the hash A and hash B, I'll get hash A, B until I get to one root. So if I had some other data here, let me see, PQ, and didn't have any other to combine with, it would move here, hash of Q, and then it would be hash of Q here until there is one sort of hash from the left hand, and then it combines with it to form the root. So what we want to do here is to form the root. So here we are going also to combine these to form their hashes as we go up the tree. Yes?
Are you trying to... Can you hear me?
Can you hear me?
Yes.
Yes. Are you trying to say that
These blocks
these blocks
down,
down,
they're not linked to
they're
each
not
other.
linked to each other?
They're independent.
They're independent.
Yes. So yes, the blocks down are independent. I think initially it helped me since I was drawing the data block boxes. This will become A, B, C, D. Okay, so um, I don't know what is happening to this. So the reason I've drawn this Merkle tree is for us to really have like a deep understanding of it. And so what I mean by that is, given some parts of the Merkle tree, let me say, if I have the hash of G and H, that will simply mean that without knowing the hash of G and the hash of H, if I have the hash of G and H, then I can know the hash of G and the hash of H, because the hash of G and H was derived from adding the hash of G and the hash of H. But if I have also the hash of G, I don't need to know the data G, because G, there's only one data that can create hash of G. From hash of G, I can find data. Yeah, should I repeat that? So one of the things we were saying here, that given nonce, if this is the hash, when I change this, maybe with 3, I'll have to mine a new nonce so that it equates to the previous hash. If I'm to take it, if I'm to take this analogy in this scenario, I think having G, like having hash of G, will in a way give me like the data G, because there can only be one hash from the data called G. So this means that just knowing parts, right parts of this tree can help me like create the entire tree and the entire data, and I don't need to have that data all stored. As long as I can verify or prove that that data was part of the hash function, then that means that that transaction is a correct one. And when we go to this, specifically to this, for you to know the entire data, or for example, if to calculate, as long as you have a hash of A, B, C, D, E, F, G, that means that you can derive all the hashes of A, B, C, D, hashes of A, B, until you reach to the atomic hashes. And then you can also derive A, B, C, D, and E. So if I'm given A, B, C, D, and E, that means that the left branch of that tree is already sorted up to the second last node. What we have in trees, as we saw here, we have a root, a Merkle root. We have the nodes and the leaves, then the data. So this is upside down, but the root is the one that is up here. So this is a root. So with this and this, I will not need to know the root, because I can generate the root with both branches on the left and on the right. So that means that if I have hash of ij, I don't need to have the hash of I and hash of j. And if I have the hash of A, B, C, D, E, F, G, H, I don't need to have hashes of this individual thing. So with just these snippets, I can know the entire data. If this was a block, I can generate all the entire hashes that were in that block by simply knowing the hash of ij, hash of L, and hash of mn, p, and here hash of k. Yeah. So with hash of k, I can find the data k, but knowing this will give me hash of k and L, and knowing hash ij with this, then I'll get hash of I, j, k, and L. Even if I didn't know this, but having hash of mn or p at this level of the tree will help me have this and this to generate hash I, j, k, l, m, n, or p. And with this and this, I can form the root. So if I'm given the root and the right hash of the branches, of some of the branches, I could end up generating all the data in the Merkle tree when need be. probably, for example, this, it could be a transaction. Because the biggest thing to prove in the blockchain is to prove that a given transaction was right or it was true in a given block. Yeah. Hope that thing like that has been sort of understood. So we continue. Do you have a question? Okay. So if we go back to this, so here we have transaction A, prove that transaction E. For example, I think here, so verifying validity using Merkle root. So it's all the same concept. When these transactions get rolled up into a block, the block header would contain the Merkle root. Hash of ABCD, the Merkle root, which is hash of ABCD. So here I think we had ABCD. So we are proving that an added transaction, an injected transaction E, is a false transaction. All miners have a copy of all transactions so far, and therefore all the transaction hashes, any miner can rebuild the Merkle tree on demand, which means that every miner can independently arrive at the same Merkle root for the same set of transactions. This allows any miner to verify a fraudulent transaction. Let's say someone tries to introduce a false transaction instead of transaction D. Let's call this transaction E. Because the transaction is different from transaction D, the hash will also be different. The hash of the transaction E is hash E, as introduced here. Yeah. The hash of C and E together is hash CE, which is different from hash CD. When the hash of AB and CE are hashed together, you get hash ABCE. Since hash ABCE differs from hash ABCD, which was the hash of the Merkle root, we can conclude that the transaction E is fraudulent. Yeah. So a miner can recompute the Merkle root in their own block and try to publish that version to the blockchain. But since every other miner has a different Merkle root, the fraudulent miner is easily rejected. Okay. So in deterministic, the same input always has the same output when passed into a hashing function. So benefits of Merkle trees. Merkle trees allow for quick verification of data integrity. The disk space used up is very little compared to the entire set of transactions. The Merkle root is included in the block header for this reason. So if you have two sets of identical transactions, verifying that they are the same with a Merkle tree is faster than verifying the transactions individually, one at a time. One can verify that a block has not been modified by only knowing the Merkle root. So use cases, IPFS gate, verification of presence in a Merkle tree. I think this is what we have been trying to do. So yeah, for this you would only need this, the blue ones, and yes, so if I have this and this, I can get this, then this with this, I'll get this, and this hash of this with hash of this, I'll get this, and I hash this and hash this, then I'll get to the root. Okay, so we have use cases in smart contract. Since the verifier does not need to store the entire Merkle tree to verify if something is a part of it, Merkle trees actually come in quite handy for certain things. So previously we created the whitelist that stored user addresses in a mapping. While that approach works, storing that data in smart contract storage is by far the most expensive thing you can do in terms of gas. So what if you had to store 1,000 addresses or 10,000 or 100? In this kind, when we want to do an airdrop, at this point, utilizing smart contract storage directly is just not feasible and can easily cost millions of dollars to whitelist people. On the other hand, you could build a Merkle tree and store the Merkle root value in the contract. Yeah. a measly byte 32 value. In this scenario, the contract is now there, and users who wish to use their whitelist spot for minting maybe NFTs, let's say, become the provers. I think the contract is the verifier, and then those who want to mint become provers. You will find that these terms, for example, in Stacknet, there is the prover and verifier. Almost L2s, what they do, they have provers and verifiers, and this is where like those terms start coming from. So proving that they are indeed part of the whitelist. Yeah. So with that, I'm not going to go into that example. Probably we are going to have, this is, I think, is already part of the so this can be an example of Merkle proof. So if you want to see the code of creating a Merkle proof, but you can also go through that example. I put it in the rise up. So yeah, that is the article. So yes, this is the one for Open Zeppelin. You can go through it after here. It is one I wanted to go through, but I think it is not feasible right now. So yeah, each one of us can go through it and then shall have feedback. So what I want to do next is like expand this a bit further, and I can call it Merkle proofs. So probably blockchain in depth. I think so having such an example, we can take it a bit further, and the reason for this lecture at this moment is that I want to really ignite our passion in research. Probably you could be thinking creating an L2, there is no reason, but there are always reasons, because there are very many things to optimize. So you could create maybe a specialized L2, you could create a bridge, trustless bridge, and things like that. So for that, I'm going to start with okay. Yes, I'll come to this topic. So let me start with this. So this is an article from Polytop Labs. Yeah, by Seunlan Leg. This is the one. Yeah, but I want it in black. Okay. So state machine proofs. Let me add it in the rise up. Should we have a break? So let's continue. We continue? Okay, so yes, state proofs are a critical primitive of blockchain stack that enable things like trustless bridges, off-chain light clients, and that can access on-chain data in permissionless and secure manner, as well as modular blockchain architectures where the execution layer can be decoupled from the consensus layer. So I think from here, let's know what the consensus layer. So the execution is simply where the transactions are happening, and the consensus is where the set of rules are happening. But what exactly is it? So in this article by, okay, let me add it in the Rise Up. I encourage us in our free time, to go through these articles. Yeah, so in summary, what is a consensus mechanism? What does game theory play like in a blockchain? We hear this term consensus, game theory. And what are the main characteristics of a good consensus mechanism? Blockchain as a catalyst for fund social good. So yes, there is. So here is what we want. What is consensus? It's a concept that describes an agreement produced by consent between all members of a group or between several groups. So then that consensus differs from a majority, because for there to be a majority, there must be a minority that disagrees. While in consensus, by definition, there is no disagreement. Consensus is simply following a set of rules that have been put. So to understand this better, think of presidential elections where whoever is elected needs the vote to reach a majority. Disregarding the feelings of well-being of the minority. On the other hand, a consensus ensures that voters reach an agreement that benefits the group as a whole. So, have you ever thought about the value of reaching consensus in a polarized society? Isn't it unity and trust that makes great nations thrive? So blockchain as a catalyst for profound social change. Blockchain, which most people know as the technology that makes cryptocurrency transactions possible, is gradually taking on a new role. A new role that will bring about, for the first time, a change in the ownership of those who confer trust on business relationships, making it possible for new business models and markets to emerge. Its architecture is capable of removing a portion of the power that used to go to intermediaries and trust validators, transferring it to the people who actually take part in a given transaction validated on a blockchain. So in other words, blockchain technology allows direct interaction between strangers or people who don't know each other in a distributed network and without the need for traditional validator of trust, such as corporations, institutions. So in this context, blockchain technology is a catalyst for profound social change, because for the first time in history, people can interact directly and in real time without the need of intermediaries. How does that even work? So that's what does the game theory play in the blockchain. Consensus mechanisms, also known as game theory, are the basis of all blockchains. So when you hear game theory, it is simply consensus mechanisms. So, but to understand this better, let's take a step back to understand why blockchain is known as the trust machine. So I think we can start from game theory from crypto economics. So it is the consensus algorithm that on blockchain platforms formed by decentralized network defines the rules for devices spread all over the world to reach an agreement, which is consensus, making it possible for network without intermediaries to function without fraud and without being corrupted. So consensus is achieved when enough devices agree on what is true and what should be recorded on a blockchain. Therefore, consensus algorithm, also known as game theory, are the set of rules that describe how communication and data transmission works between electronic devices participating in a blockchain network. I think okay, so since the article is getting done soon, cryptoeconomics is a new field of knowledge that brings together economic and computer science to study the decentralized market and application that can be built by combining cryptography with economic incentives. Yeah, it's an economic incentive that ensures that validators on a blockchain network like Bitcoin behave in favor of security and try to hack, defraud, or corrupt the system by double spending. By double spending. So one of the biggest problem in computing double spending is the risk of a digital currency being duplicated and used on more than one occasion. So this is an attack that can affect distributed networks due to their decentralized nature. Just as fiat money is exposed to counterfeit notes, digital currencies were prone to the fraudulent act and therefore required an intermediary to validate transactions on the internet. It is the economic incentive implemented by consensus algorithm that motivates participants to act in the interests of the blockchain network rather than their own self-interest. So consensus mechanisms set the rules that economically incentivize the participants of the blockchain platform to verify transactions and reach an agreement, which is consensus on what is true and should be recorded on a distributed network. So along these lines, the proof of work mining on the Bitcoin blockchain is the first consensus algorithm that has solved the double expense, making it possible to transfer value in digital form without an intermediary, introducing a reliable network into the decentralized system, cryptographically protecting data and minimizing the risk of fraud. On the Bitcoin blockchain, encrypted transaction assertions are delivered by miners via proof of work consensus. This system effectively combats. Okay, so we have a view of what consensus is. Any questions?
No.
So we can keep going on. So one of the ways, one of the descriptions that we can give a consensus is simply that set of rules that, because when you remove the consensus mechanism from a blockchain, it becomes a distributed system. But when you put the set of rules and then all the people that are running a copy of the blockchain can prove that a transaction was true based on those set of rules, then you have a blockchain working. So, and this differs on why blockchains choose consensus mechanism like proof of work, proof of stake, nominated proof of stake, proof of authority, proof of liquidity. So based on what you are doing, you can choose to create a blockchain with its own consensus. So this is going to be our last article, and as we have been looking at it, we start by the consensus layer, because I think it will really open us up to what really blockchains are if you want also to innovate or create your own blockchain, layer 2 or a client, things like that. So we on state proofs, and they're also part of something like the Merkle trees, as we shall see. So state proofs are critical primitives of the blockchain stack that enable things like trustless bridges, off-chain light clients that can access on-chain data in a permissionless and secure manner, as well as modular blockchain architectures where the execution layer can be decoupled from the consensus layer. So to understand how state proofs enable these functionalities, and more importantly, what they actually prove, it is necessary to first understand blockchains as a state machine. So we've had a session of understanding the EVM, but we can have a high-level overview. So in a generalized blockchain model, we can describe a blockchain with blocks as a state machine. To create new blocks, we apply a state transition function to the state at a given block height with a transaction list, which results in some new state. This can be more formally expressed as follows. So this transaction list can be seen as a list of database transactions, where the state represents a key value database. So these transactions may create, update, or delete items in the key value database. It is important to note that in this state machine model, our state transition function returns a new copy of the database. So this means that the output of a successful transaction is fed into the input of the next state transition. So this means that the output of a successful transition is fed into the input of the next state transition. Therefore, at every new block is a corresponding state that describes the current state of the blockchain database after applying the list of transactions. So data verifiability in blockchain, data verifiability is blockchain's main value proposition. So that's why Merkle trees should click again. You have to verify that this transaction is true or false. Which is why, in order to arrive at the latest, which is the trusted state of a blockchain, it is necessary for blockchain nodes to reapply all the transactions that have been made since the genesis block. By reapplying each transaction, each participant is able to produce the new state of the blockchain. This mechanism is what allows blockchains to be considered a tamper-proof database that can be trusted by all participants. So, for example, in such a scenario, when we have S1, S2, transition S1, S2 on block B1, B2, B3. So if some transactions went to, if there was a transaction S3 complement that made this block, like, which were added to this block. So whenever these blocks like recompute the previous transaction, their computation should reach up to the genesis block, which will imply that now this block is a faulty block, and then these transactions will be verified again and pushed in another block, so that we keep the blockchain going, because there can be two blocks created at a time, but the longest block will the one that will be proved correct. And how does the longest block formed? The longest block is formed based on the consensus set of rules that we are set at the consensus mechanisms as a consensus mechanism. If the validators are those that prove that the transactions are correct, if they collide and work in their own selfish interest, for example, they want the transactions in this block to go through, if they are found out, the penalty is slashing their stake. So slashing is when the network completely cuts off or takes all the stake tokens you have, all part of the state of your stake tokens, as a penalty towards working fraudulently or selfishly towards maybe transactions that we are correct. Yeah, but there's a whole lot of things around it. This is where MAV companies come in. For example, certain entity could have maybe wants to have their transactions done first and then reach finality. They could collide with validators or create MEV things. Yeah, and that's the concept. So there may potentially be multiple state transitions for a given block, as you can see in the diagram, or have multiple state transitions. This is where the role of a consensus algorithm, known as fork choice rule, comes into play. The role of consensus in a blockchain is to tell us which sequence of state transitions are final or can be trusted. They do so by employing a combination of game theoretic and cryptographic protocols to ensure that the network will always agree on one history of state transitions and not more. So for people who are interested in building protocols, we have Manuel.
Yeah. I actually have a question. So in an instance of a hard fork,
Yes.
does that mean we lose complete contact with the previous block before the hard fork was executed?
Yes, so the previous blocks are cut off.
So essentially, if I wanted to find a genesis block of ETH 1.0,
Yes.
using the hard fork of ETH, I cannot find it.
Yes, this current hard fork of ETH, you cannot find it. You will find the genesis block will be
of ETH 2.0.
ETH 2.0. But also you can start a business. So there is what we call Ethereum Classic. One time we shall see it is also a blockchain that was formed when a hacker depleted Ethereum fund initially. So they made a hard fork, but Ethereum Classic remained creating blocks, and their token is on. So also other blockchains like BSV were forked from Bitcoin. And so we see now that the existential law of a blockchain is to prove a database that is backed by a sequence of valid state transitions. But there's a problem with our current model. Our state transition function always returns a new copy of the full database. Implementing a blockchain using this model would be prohibitively expensive. This is because we'd have to copy over the full state DB for every new block, even parts of the state that haven't changed. To address this problem, we need to optimize the size of the data needed for our state transition function, effectively making it sublinear to the size of the full database, i.e. where is the size of the full state. So one solution is to leverage a state diff, which would only include the parts of the state that have changed, rather than copying the entire state database for every state transition. So this would bring a significant space and time savings associated with running blockchain node. This state diff means our state transition produces less data and is as a result more efficient to compute. In order to achieve this state diff, we'll need to leverage a different kind data structure for our blockchain state. Let's take a detour into commitment schemes. So cryptographic commitment schemes. A cryptographic commitment scheme is one of the most powerful cryptographic primitive in a protocol developer's toolbox. So formally, a cryptographic commitment scheme allows a committer commit to some message, producing a succinct commitment. So as you look at deep into zk snacks, there is what we call succinct commitments. But this is just commitment scheme. So where such that the committer can later on reveal the message to a verifier who only has the commitment, and the verifier can validate that the message does indeed correspond to the commitment. So most of the things in blockchain, it's all about verification, a verifier, approver, or a committer, and then messaging. When you send token from A to B, it's a message. So a commitment scheme should testify to security properties. Hiding, which is receiving a commitment to a message, should give no information to the verifier about. Then the other one is binding. The committer cannot cheat in the second phase and send a different message that corresponds to the commitment. Now, given this primitive, we can use this scheme to commit to our state, such that the current scheme is a great starting point, but we need more. Specifically, we need a scheme that supports partial reveals. By supporting partial reveals, we can commit to some data and produce a proof for only a portion of that data, which can later be verified against a commitment to the full data. So with this scheme, we can reduce the size of the data needed for our state transition function while still being able to verify the authenticity of that data. Okay.
Yeah, another question.
Yes.
So in cases of validity proofs,
Yes.
validity rollups rather,
Mm.
the process of validating a transaction is done on the base layer. Because I'm wondering, would it be the layer 2 itself that does the validation, or does it deliver some kind of authentic proof that can be validated by the
So what it delivers is a proof, is a validity proof. So a validity proof is in an essence, it's like it has corrected transactions, and even without knowing what is entailed in these transactions, it has a proof that these transactions are correct.
That would be
Then that proof is then that is sent to.
But what I'm thinking, what I'm wondering is, I could send a counterfeit proof
Yes.
to the base layer.
So for example, mainly for the validity rollups, they have something called attestation, which is a 7-day period. So for them, by default, they believe that every transaction that has been made on the L2 is a correct transaction. So, yeah. So until someone or until an entity or a node runs comes up and attests and says some of these transactions are false, then that layer 2 of validity rollup will have a rollback in its own mechanism. A rollback is like going back before that transaction was submitted and then remove it, and there is an incentive for the person, for the node that attested, and then there is a penalty for the entity that, or for the wallet that put the transaction in.
So essentially, finality cannot happen until the period of 7 days has passed.
For validity proofs, that's it, like in documents, right?
And what criteria do they use? A Merkle proof to confirm that a particular batch of transactions is valid.
Yes. So we are going to see what they use. So given these algorithms, we can modify our initial state transition function, like the commitment to the state, like so, where the commitment to the set of values are in the set that would be modified by the transaction set, the state proof of the existence of the set in the original state, then the set of transactions which operate of the key value in. So most of these proofs mainly provided with a key value sort of thing. But you look at, I think, as we go on, yeah, I think let me just read it. So in this new scheme, instead of taking a full state DB as an input, our state transition function takes a commitment to the full state DB. So the values that will be modified by the transactions, a proof for these values corresponding to the commitment, and finally the actual transaction list. But instead of returning a new copy of the state DB, it only returns a commitment to the new state. This approach prevents redundant data copying during state transactions, resulting in a faster runtime for our blockchain that if we copied the entire state database every time, and indeed this is how most modern blockchains are implemented, than if we copied. Yeah. So there are many ways to implement a commitment scheme that supports partial reviews for our state, but the most robust and widely method used is a Merkle tree. So yeah, this is where Merkle tree is coming. On the part of commitment, we want to get away of just having like a very light proof instead of copying all the data to prove that, you know, this is the valid blockchain or this is a valid transaction on this block at this block height. So yeah, this is a Merkle tree. So Merkle tree is a powerful, maybe I should not leave it. I think as we started from a Merkle tree, now we are seeing where it really also joins in on the blockchain itself. So you can be coding like smart contracts, and you code a Merkle proof, maybe for whatever you want intending to do, or you can also have like this encoded in your blockchain. That's why you see some blockchains are fast, some blockchain prioritize speed. Now like validity proofs, maybe if you want to do decentralized sequencing, because in decentralized sequencing, it's like the person who relays these transactions fastest gets more clients. So that means that if you implement something that really sorts out these things quickly, you're getting more money or clients who will use your sequencer. Okay, so a Merkle tree is a powerful data structure that enables efficient verification of large amounts of data. Specifically, a Merkle tree can be thought of as a cryptographic hash function whose pre-image is a virtual tree. As such, the root node of this structure is cryptographically dependent on all internal data, and its root hash can be used as a secure identity for the data stored in a tree. So Merkle trees also support partial reviews for subsets of the original data through mount proofs. I think that we have really seen that with just these, you can create the entire tree.
So I'm just wondering,
Yes.
for protocols like Madara,
Yes.
validity proofs take up to 7 days. How can it be used as a gaming sequencer then? Because games require fast processing.
So Madara is a ZK based sequencer. So the difference between validity, so the reason they called it validity, so it's like, but Madara is a zero knowledge based sequencer because Stacknet is based on zero knowledge. So they use the ZK technology, and the ZK technology is simply you are not optimistic, like they say optimistic rollups. The reason why they started calling Stacknet, like, I think my internet is off. Okay, they started calling it validity based proof is because people used to think that proving zero knowledge cannot be used for scaling. Yeah, so, but ZK can also be used for scaling. What happens in ZK is that you have something that is inside that you don't know, but you provide the proof that it is there. So you have transactions that you don't know. It's all, yeah. Actually, Merkle trees look like they can, if they could completely shield what is inside the Merkle tree, or partially, but then someone can prove that a transaction is part of that proof that has been given, then they can also be used as ZK. And of recent, of course, Optimism introduced a platform where ZK proofs can be submitted and allowed. Yeah. Hello. I don't want to use this account. Yeah, so let me share my screen. So yes, we're here. And however, it's important to note that Merkle trees only support flat lists of data. In other words, a Merkle tree on its own cannot be used to encode key value pairs. Yeah, so maybe I can start from here. A Merkle tree is a powerful data structure that enables efficient verification of large amounts of data. Specifically, a Merkle tree can be thought of as a cryptographic hash function whose pre-image is virtual tree. Yeah. So as such, the root node of this structure is cryptographically dependent on all internal data, and its root hash can be used as a secure identity for the data stored in the tree. So Merkle trees also support partial reveals for subsets of the original data through multi-proofs. So, but however, they support lists. Okay. However, it's important to note that Merkle trees only support flat lists of data. In other words, a Merkle tree on its own cannot be used to encode key value pairs. So, to take advantage of the Merkle trees support for partial reveals for key value data, we need to combine the conventional Merkle tree structure with another tree structure that allows for key value encoding. Yeah, then we can come to Patricia trie. So a Patricia trie, also known as a radix trie, is a kind of array search tree which is used for efficiently looking up items in a database. So it achieves on search complexity by encoding the keys in the trie nodes along the path to the data. Unlike conventional tries, a Patricia trie only creates a node for each unique prefix of its keys. So this reduces the amount of memory required to store the trie and allows for faster lookups. So we know Merkle trees support flat lists, but we have Patricia trie that support key value pairs, but they only used for searching. The Patricia trie can only create a node for each unique prefix of its keys. Yeah, so they only create like nodes for the prefixes. So probably we need to combine these, I think. So Patricia tries were first described by this Morrison and have since been used in a variety of applications, including IP routing, tables. Yeah, so for example, for this is how they do it. So if these were put in a Patricia trie, you see that you can, from every angle, parity, participate, parity. So parity, participate, party. And then, yeah, that's how you form the data from a Patricia trie through prefixes. Okay. So they are a powerful data structure that can greatly improve the efficiency of searching and retrieving data from large database. So then we come to Merkle Patricia trie. So because Patricia trie will bring in the uniqueness of, having the key value thing, and then the Merkle trees are very good at partially revealing data. So there was something called Merkle Patricia trie. So the Merkle Patricia trie was invented by Dr. Gavin Wood, co-founder of Ethereum. It was first described in the Ethereum yellow paper. This data structure combines the Patricia and Merkle trees into a single tree, which has the ability to store key value items, while still allowing for Merkle proofs. So we really, the thing is proving, yeah. So while still allowing for Merkle proofs. Okay, we are somewhere. So this is the last article we are having. No additions. Merkle proofs, for Merkle proofs, where represents the arity of each node and represents the number of leaves in the tree. So the yellow paper prescribes an arity of 16, but using other arities is also possible. So yes, this is one of the ways that proofs are given. So hash function, so we have the one we still have in the Ethereum blockchain is Ketchup256 as a hashing function. Yeah, I think this I've shared also this article in this. My aim is, have I shared it? My aim is to break the fear down and if those that would really want to contribute, for example, to the clients, Geth, things like that, and when you know like where to start from, what is. If you want to fork Nethermind, these are, I don't know why this. Okay, force reconnect. Okay, so as it is reconnecting, we can continue. And also get a broader view, like you can create a new specialized blockchain that is serving a better purpose in your own direction. Probably gaming, I don't know, or rapid transactions, or in Nasdaq. So yes, the yellow paper describes 3 kinds of Merkle Patricia nodes. The leaf node. So a leaf node can be thought of as a 2-item tuple, where first item corresponds to the bytes in the key, not already accounted for by the accumulation of keys in the branch, and extension nodes traversed from the root. The second item corresponds to the actual value held at the leaf node. So the hash of a leaf node is gotten by concatenating its partial key with the hash of its value and taking the hash of the concatenation. Concatenation is a union. Yeah. So we said there are 3. The paper describes 3 kinds of Merkle Patricia nodes. One is leaf node, second is extension nodes, and the third is a branch node. So okay. So compact Merkle Patricia proofs. So the Merkle Patricia trie was further modified for substrate and Polkadot, resulting in more compact state proofs by eliminating extension nodes. So instead, so the reason I go through this is you can really see how innovation is moving, because we have some L2s that forked the substrate. We have things like a Veil protocol, which provides a data availability layer for all L2s. It's a fork of the substrate. You have a substrate also having modified some things to create the substrate from Ethereum. So it's like when what you could call a mistake in one research could be the golden goal that creates another blockchain. So we are on compact Merkle-Patricia proofs. The Merkle-Patricia trie was further modified for Substrate and Polkadot, resulting in more compact state proofs by eliminating extension nodes. Instead, Patricia keys were introduced to branch nodes. So this means that branch nodes can hold accumulated partial keys, which eliminates the need for a dedicated extension node. With this modification, state proofs are effectively compacted and less nodes are required in state proofs. Applications. Now that we have a comprehensive understanding of state proofs and the underlying concept of blockchains as a verifiable state machine, we can now delve into the various applications of state proofs. Modular blockchains. Only one article. Yeah, it's going. So, as alluded in the previous section, the consensus and the state machine are two separate sub-protocols in the blockchain stack, but conventionally they have been combined into one monolithic protocol. I think now they are separated. However, ongoing research and development has demonstrated that significant scalability improvements can be achieved by separating the two protocols. So in this new approach, a single consensus layer, like consensus layers that we have, I think we have Nimbus, Geth, Wraith, Nethermind. Consensus layer is responsible for coming to consensus about the state of multiple concurrent state. And actually Nethermind accepts interns. You can also fork Nethermind and create your own client, which is highly encouraged. So yes, we can have a consensus layer and have many blockchains. Independent state machines. So state machine is its own blockchain. You can also have an opportunity, if you have the same consensus layer, for this embedded state to communicate between each other, like this thing we see in Polkadot and in Optimism, where you have all these blockchains like Base and Lisk and all using the consensus layer of Optimism. Okay, this allows for many benefits such as high transaction throughput and as a result, faster processing of transactions. Additionally, the separation of the two protocols allows for greater flexibility in network design, enabling developers to create more specialized blockchains for application-specific purposes, known as app chains. Yes, now we have things like EduChain, which is an app chain, or an L3 built on top of Arbitrum. Things like that. I think even to some extent, there's some layer 3s that are built. Anyway, let's continue. So this modular design was first pioneered by Dr. Gavin Wood as 2016 in a revolutionary white paper for the Polkadot network. So this design facilitates the provision of consensus by a blockchain to other blockchains by validating its state transition through the use of state proofs. Polkadot parachains and optimistic L2s on Ethereum both use state proofs to achieve parallel state machines running on a single consensus layer. In this new architecture, the state machines commit their blocks, which include the commitment to the new and old state, as well as a state proof for the part of the state modified by the block. So this state proof is also referred to as state witness or proof of validity, depending on who you ask. So in case of Polkadot, the Polkadot relay chain re-executes parachain blocks with their given state proofs to ensure that only blocks with valid state transitions are finalized by the Polkadot network. This is accomplished by using sub-protocols referred to as availability and approval. On the other hand, Ethereum doesn't re-execute optimistic L2 blocks. Instead, it relies on off-chain parties to re-execute the L2 blocks. If an L2 block is posted on Ethereum with a state commitment that doesn't match the actual value calculated after its blocks are executed off-chain, the L2 block can be challenged. This is done by forcing its re-execution on-chain so that its real state root may be derived. Unfortunately, this is also why withdrawals from optimistic L2s take at least 7 days. The reason for the delay is to mitigate any censorship attacks that may arise and give honest parties enough time to challenge invalid L2 blocks. However, with the rise of proof of computational integrity schemes, it becomes possible to enforce valid state transitions by producing a proof that the state transition was executed correctly off-chain. This allows the consensus layer to verify a succinct proof that validates the state transition formally. So where is the proof of computation integrity? So as you know, like Stacknet has proof of integrity. But this is proof of computation integrity. And even this is also one of the reasons we are diving into this subject. Like, you can come up with research labs, and maybe you're searching proofs, you're getting proofs and proving whether they are valid, because there is a reward and there's an incentive to, if you can prove that a proof is invalid, if you can give a challenge, there is really a computational reward or anything in that regard. So this would scale blockchains even further as the consensus layer no longer needs to be aware of the state proof of the actual transactions behind the transition. Many teams are actively working on this problem, but seeing as this is a relatively new technology, we should not expect robust implementation any soon. Light clients. We are almost at the end of the article. So light clients allow for computationally constrained environments such as mobile phones, IoT devices, or even another blockchain to read the state, try and write, submit transactions. This only works for off-chain light clients to a blockchain network. An off-chain light client achieves this by connecting directly to the P2P network of blockchain nodes rather than relying on centralized or even worse decentralized RPC providers. A light client, unlike a full node, does not track the state transition of the blockchain network. This greatly reduces the amount of data it needs to download and store. Instead, light clients only track the blockchain's block headers and consensus proofs, which are usually small enough to be validated. They use the headers and consensus proofs as a source of truth for the latest finalized state of the blockchain. Given that a blockchain header contains a commitment to the blockchain state. So, in order to read the blockchain state in a trustless manner, light clients can request state proofs for the items in the state try that they care about from full nodes who actually maintain the full blockchain state. By validating the state proofs of the items against the state root instead of a verified block header, they are able to securely access blockchain data backed by full blockchain security. Unfortunately, light clients today are essentially parasites. Since their state proof requests add extra networking and computational load on full nodes. So that's an opportunity. So this is because full nodes must traverse the state try in order to serve these requests. Therefore, if we want to maintain a healthy blockchain network, especially in the future where millions of people will use light clients to access the blockchain state, it is necessary to introduce a light client data incentivization protocol that incentivizes full nodes to respond to these requests from the light clients. trustless bridges. So this is from one topic, which is Merkle trees. You can see that it spans deep down into the research that birth and still moving our blockchains. So trustless bridges enable the secure transfer of data and assets between two separate blockchain networks. These bridges rely on the security assumption of the sending blockchain by observing and verifying its consensus proofs on the receiving blockchain using a light client. This eliminates the need for attesters, oracles, or other kind of trusted intermediaries. In order to achieve this transfer, the outgoing assets and all data are stored in the state trie of a connected blockchain. So the proofs, this allows us to obtain state proofs for the transfer. So you get the state proofs for the transfer, which proofs can be verified on the other independent blockchain, so which can then be verified by the counterparty blockchain. Once verified, these state proofs are used to authorize the minting of the transferred assets or the delivery of the cross-chain message. Interoperability allows for users to leverage the unique features of different blockchain networks. For instance, a user might want to transfer their assets from a public blockchain network to a private blockchain network, where their assets can be shielded and the transactions encrypted in such a way that they are obfuscated to the external world. So trustless bridges also allow for competitive protocols to accumulate user assets and provide better services to users. This competition derives innovation and motivates blockchain networks to improve and differentiate themselves from others. Additionally, trustless bridges promote collaboration between different blockchain networks by enabling developers to create more specialized blockchains for application-specific purposes. So in summary, I've shown how state proofs are critical primitives for securing interoperability and scalability. As such, ongoing research and development is seeking to make them even more efficient and concise. So this will allow not only improve the performance of blockchains, but also make them more accessible to a wider range of users. In an upcoming article, delve deep into these developments and explore their potential impact on the future of blockchain technology. So there are references here you can read.
Could you please share?
Everything has been shared in the Rise Up. And so there is this program by Ethereum. I think Ethereum, you can join Ethereum core developers. They have even an incentive for it. I think it happens once every year. And these are some of the things you research into. Actually, most of the blockchains get one component and build blockchain and build value around it.
Please share the link to the program as well.
The link to the program, I don't know whether it is still on, but if I research and see, I will see.
So just one final question.
Yes.
So in the context of a bridge, when you say there's a state proof that is being verified on the receiving blockchain, is it receiving a proof that tokens are being burned or locked away somewhere before it can mint an equivalent on the new blockchain?
So I think if it is a bridge, if it is a trustless bridge, we should know the type of proofs that are created by the counterpart block or by the sending block. So for example, maybe if it is Ethereum, you should know what proofs it accepts or it emits when there's a correct transaction. Then maybe you can use that proof on Polkadot or on another chain. Otherwise, if it is not that, then that's why we have oracles, which we don't know what they do, but Yeah, because if it is trustless, we must have a proof that actually assets have been, yeah. Hello, Mr. Ronnie. How is today's session?
I don't think it was bad. I was following, but I joined very late, like an hour into the session. But it was good.
All right. I think upcoming sessions we should talk about oracles deep, and we should do some code. But yes, this session is really good for you to dive deep into blockchains, into building like huge things. Yeah, who else is here? Arthur, how are you, Arthur?
I'm good. I'm resurrected from the dead.
Yeah, you're welcome. We keep on. Damba, how are you?
I'm great. I'm doing fine.
All right, great. Meeting everyone. I think for now we can stop here. We shall not do code. Yeah, see us in the next one.